In this class, we study linear momentum conservation. Linear momentum conservation is the direct consequence of the Newton's third law, and it has various applications, including collision problem. Let us recall the definition of linear momentum. This definition is true for both non-relativistic theory and relativistic theory. In relativistic theory, we have m dot is in general non-zero. But in this today, we simply restrict ourselves to the non-relativistic case in which the center of momentum frame is identical to the center of mass frame. When we study relativity, it is not really true, and it's better to consider the center of momentum frame instead of center of mass frame. However, to simplify our analysis, we restrict ourselves to the non-relativistic case, in which m dot is always zero. Okay, if m dot equals zero, then linear momentum can be written in the form mass times position vectors time derivative. The expansion will give and we consider the case this contribution vanishes as the mass times mass times the velocity is the linear momentum. This is true, but this one we do not want to use. Okay. If we consider the fact, if we consider m dot equals zero, then force is mass times acceleration. In relativity, you have to use the correct definition, linear momentum's time derivative. But if we consider this case, time derivative of mass times velocity, m dot equals zero, so mx double dot. Okay, force can be expressed in terms double dot in terms of the product of mass and acceleration. Because m dot equals zero in our case, it is just double time derivative of mx or a single time derivative of mx dot. That is momentum's first order time derivative. Linear momentum of a system of particles. If we consider many particles, each particle has its own mass and its position. And if we take the time derivative, we have linear momentum of a single particle. That is pi. If there are n particles, then we have to sum all of the momenta of n particles, and that is mi xi dot sum over I, where I runs from 1 to n. We define the total linear momentum in this way, and if we assume mi dot and capital M dot, capital M is the total mass of the system of n particles. In that case, total linear momentum is by definition this, or I is missing. So I have corrected this typo. So linear momentum sum can be expressed as if we pull out the time derivative outside, sure, we have to impose these conditions. Then this one is, we can make use of the definition of a center of mass. Definition of a center of mass. So this sum is center of mass times total mass, right? And then we just take the derivative again, and we assume capital M dot equals 0. Then we end up with the fact the center total linear momentum is the total mass multiplied by the velocity of the center of mass. This is a very important result. Newton's laws of a system of particles. If we consider two particles, they communicate each other, the two forces cancel. The two forces cancel exactly. That is the Newton's third law. And if I substitute J equals I, we find that the self-interaction vanishes. It is impossible to have a self-interaction. Therefore, if there are many particles, then a single particle, ith particle, accepts the force from other particles J that is not equal to I. That is called internal force. Internal force is the sum on the ith particle is the sum over J that is not equal to I. As well as the internal force, there is external force. External force is the source of the external forces out of this system. There's an n particle system. Outside of the system, it can apply some force. That is called external force. So the internal is within a system, external is out from outside of the system. When we compute the net force on a system, on an ith particle, then the net force should be the sum of all of the internal forces and all of the external forces. So ith particle's net force can be decomposed into external contribution and internal contribution. For internal contribution, there are n-1 contribution at most, because there is no self-interaction to itself. Why don't we compute the total net force on this ith particle? And if we sum over the I from I through n, then F net is the net force on the system of particles. And if we compute the net force on the system of particles, then we have to add all of the ith particles' net force. And ith particles' net force is sum of the external force on that particle and the internal force on that particle. Here, ith particle accepts a force from jth particle, and we can express this one as sum J applies I and I applies J, and I is not equal to J. Then this one, sum of this is just 1/2 of this because of symmetry. So we have 1/2 and sum over I, both I and J, for I applies to J and J applies to I. However, Newton's third law states that any pair of forces for the two particles interacting each other, it is vanishing, absolutely zero. Therefore, the net force on the whole system is the sum of the net external force on every particle. Therefore, we remove this internal force contribution and keep the external contribution only. That is the sum of external forces on every particle. The cancellation of the internal force is regardless of the fact whether the force is repulsive or attractive. It is always true. Next, we consider linear momentum conservation. The net force applied to a system of n particles is now identified to be the net external force on the system of n particles. The net force on the net external force applied to the system of n particles is the algebraic sum of net external force on every particle. Therefore, the total linear momentum capital P is total mass multiplied by the velocity of center of mass. And if we take the derivative, we have this. And this is the what? Net force on this system. And if the net force on this system is the same as a net external force, then the time derivative of a total linear momentum of a system of n particles should be the same as the net external force on this system of n particles. If there is no net external force applied to this system of n particles, then this one becomes 0. That means the total linear momentum P is conserved. If F net external is 0. Okay? So any interaction due to the internal force among the participants of a system of particles does not contribute to the change of the total linear momentum. The center momentum frame. The center of mass is now defined to be the weighted average of the position of n particles that consisting of that construct the system of n particles. If we multiply the total mass both sides, then m times xcm, that is sum of this. Here we need to remove this one in the denominator. So we have corrected the typographic errors. So this should be in this way, and the previous formula, this one was also wrong. The m1 plus m2 in the denominator has been removed. Okay, so we consider this total linear momentum, and we apply Galilean transformation from having some velocity, relative velocity v. So in this new reference frame, every velocity should be subtracted by this amount, and after we subtract this, total linear momentum should be subtracted by capital M times velocity. We have the frame where this value becomes 0, when p prime equals 0, so the frame is called the center of momentum frame. In the theory, with m dot equals 0, the center of momentum frame is identical to center of mass frame. However, in relativity, in which m dot is not equal to 0, in that case, center of mass frame is not a good reference frame. Instead, center of momentum frame should be considered. However, in non-relativistic theory, the two frames are identical to each other. Exercise. Two particles of capital or mass capital M and small m. They were initially at rest with the distance capital D, but at some point they, without any external forces, they approached together, and then there was an interaction point at which where they collide, they make a complete stop. Then where is the center of mass? Because there is no external force at all, the center of mass has the same velocity forever. However, at some point, there was a collision and they made a complete stop. That means their center of mass is placed in here. And even before the collision and after the collision, the center of mass is always at rest at this point. Therefore, we have a constraint that the center of mass is this point. If we write down the center of mass, xcm, that is minus x capital M and plus y small m. This is the coordinate of center of mass, and we know this is a 0. And then our initial condition is x plus y equals d. We can rewrite this one as minus m product of two row vector and column vector, and this one is a 1 1. This is a 0, this is a d. Therefore, our linear equation is a minus m 1 1 and xy equals 0d. The answer is inverse matrix of this, and we know how to compute the inverse matrix. Determinant must be non-zero. Determinant is minus m plus m. This is the determinant. So 1 over determinant, and exchange these two and attach a negative sign on the off-diagonal piece, and then finally we multiply 0d to arrive at this. We know the sum of these two, we can check the final result with the initial conditions. We substitute these two, we find that everything is fine. And actually this is the point, this determines the point of internal division with the m and n with the ratio. The next problem is we have two particles. In between, there is a spring. I don't know how much they have been compressed, but anyway, they are still at rest, and they are combined together, stick together, and moved with the same velocity with this vcm. And at some point, the band is suddenly broken, and they these three pieces with moves with different speed, and we assume that this is uh, after separation, this one does not have any kinetic energy to simplify the problem. All right. If you consider this problem at the CM frame, everything is very simple. So why don't we boost the system to have this VCM equals 0 at the center of mass frame or center of momentum frame? This one acquires VCM minus V minus VCM, and this one has V minus small v minus VCM. Okay, and what was the initial velocity of the two particles? Initially, they were 0 and 0. Okay, what is the total linear momentum of the whole system? Initially, it is 0 plus 0 equals 0. Finally, it is 0 not 0, capital M, V minus VCM, small v minus VCM. Linear momentum must be conserved, equals 0. This one gives a very strong constraint. In such a manner, we can make use of the center of momentum frame or the center of mass frame if m dot equals 0, that is non-relativistic limit, to simplify the calculation. This is another example. I don't want to explain every detail, but in here, you have to identify the fact that total linear momentum changes. Because, why? Because of gravitational force is external force. External force. So, what is the net external force? That's an important problem. The net external force applies to the system, and the system accelerates, and the centrifuge X of Cm has a certain non-vanishing acceleration. That's the key point of this problem. To solve this problem, you might want to go to the center of momentum frame or center of mass frame. So initially, let the two body move back to back with the vanishing velocity. When vanishing, initial velocity of the vanishing initial total linear momentum. And after that, the whole system, two body all together, accept the gravitational acceleration in a single direction. So in this system, total linear momentum is not conserved. However, total linear momentum can be computed in a very easy way because the center of mass accelerates due to the external force that is constant. Okay. Next, we consider impulse linear momentum theorem. This is the case when, in general, in any case, this one is valid, but mostly we consider the case when the interaction happens during a very short time. So effective delta t is relatively short and the force is relatively large. Anyway, before and after the interaction, we assume the particles are free. This is mostly for the collision. The collision is two particles, colliding particles were initially free particles, and for a short time they interact, and in the final stage, they return to the free particle state. Okay? Anyway, during this interaction, they communicate each other one particle applies the internal force to the other particle, and the other particle applies the force in opposite sense, but the magnitude is the same. Anyway, this one is called momentum transfer because the initial P1, first particle's initial momentum and first particle's final momentum, they are different. Second particle's initial momentum and second particle's final momentum, they are different. The difference between the two, first particle's final minus first particle's initial momentum, is first particle's momentum change. And the other one is P2F minus P2I. Because the interaction is between the two particles only, this is an internal interaction. Therefore, the system, the total sum of the change of each particle's momentum, it vanishes. So linear momentum conservation says the sum of these two must vanish. But if you look at a single particle only, then there should be some change. Single particle, then it accepts the force during a certain time. There is no force. This is force. Force is positive force is applied during the time of interaction. Momentum changes. It gains the momentum, and interaction finishes. After that, it goes with the same velocity. So it is a free to free. But for a short time, there is interaction, and during the interaction, force time integral of the force is the change in the linear momentum. So as an exercise, we consider the collision of two particles, and they make a complete stop. This gives a very strong constraint. The center of mass is here, assuming that we do not have a size of the two particles. So total linear momentum of the whole system is a zero. That must be the same as before the collision and the same as the state after the collision. Total linear momentum is mv plus small mv. This one is 0. Total linear momentum, capital M v prime plus m v prime equals 0. Because the total linear momentum is conserved during a process in which there is no external forces apply. Linear momentum conservation in collisions. Collision has the initial state and final state. Initial state and final state, the two states consist of free particles. And the final state is also free particles. Only during a very short time, they interact with each other. And we assume that there is no external forces. No external forces, the total linear momentum P is conserved. Total linear momentum is conserved, so if we consider 2 by 2, two free particles interact with each other for a short time and becomes two final state particles, then initial state momentum of the sum of the two particles, this is final, Sum of the momenta for the initial state particles should be the same as the final state momentum. That is the total linear momentum that must be conserved. In terms of mass and velocity, we can write this expression this way. As we have already considered, total linear momentum is 0 in this case. Next, we consider the total kinetic energy of a system of particles. Total kinetic energy, that is the sum of all of the kinetic energy of particles. Because the position of a particle, we introduce some new variable. Position of a particle. Particle has a position from the origin, xi, there is a mass I. If there are many particles, there should be some center of mass. We say this is xcm vector. And we define the relative position of the ith particle relative to the center of mass to be xi bar. Then this one shows the position vector. We can take the time derivative everywhere. Then velocity velocities still have the same relation. So velocity of ith particle is the velocity of the center of mass plus relative velocity of the particle relative to the center of mass. That is xi bar dot. If you square, it is something like a plus b vector squared. That is a vector squared plus 2a dot b plus b squared, where a is the center of mass velocity and b is the relative velocity of the ith particle relative to the center of mass. So square is the center of mass velocity squared. This square is the square of the relative velocity. And in the middle, the crossing term is the center of mass velocity is common to everybody. And we can pull this xcm dot out. So xcm dot, this is a scalar product. And the velocity of the relative velocity of the ith particle multiplied by its own mass. However, this crossing term is exactly 0. Let's see why. mixi bar dot, I can pull this time derivative out. Then it is mixi, and this is the relative position, the relative velocity. After pulling out the time derivative, it is relative position relative to the center of mass. We know this mixi sum is sum of I, that is the total mass multiplied the center of mass position vector. And if we can sum this mi outside, that is the total mass. So the same thing is subtracted, therefore exactly 0. So this crossing term vanishes exactly. Therefore, the total kinetic energy of the system of n particles is a sum of these two. And this one, we can sum this mi. That means this. So this is the point particle's kinetic energy, whose mass is a total mass and placed at the center of mass. It's something like there is no structure at all. The second piece is the kinetic energy of particles relative to the center of mass. So we say it is internal kinetic energy. Total kinetic energy is the sum of point particles' kinetic energy whose mass is the same as the total mass of the system, whose velocity is the same as the center of mass velocity. The single particle energy plus relative motion relative to the center of mass. So this is internal energy. If there is no relative motion of the particles relative to the center of mass, this one may vanish. If it is not the case, this is a positive definite. If there is relative motion relative to the center of mass, then the kinetic energy, this relative kinetic energy, this internal kinetic energy does not vanish. So it is internal. That's the reason why we call it internal kinetic energy. The internal kinetic energy of a system of particles. Total kinetic energy of the system is now the simple sum of two contributions, and this internal energy is a kinetic energy relative to the center of mass. Elastic and inelastic collisions. Actually, if two particles collide, sometimes they stick together. We call this one is inelastic because, for example, two identical particles collide. That means initially they have kinetic energy, but the total linear momentum P1 plus P2, if they make a head-on collision, it is zero. But initially they have identical mass and identical momentum with opposite direction. This is the initial kinetic energy. However, at the final stage, if they stick together, still this one is the same as a P1 prime plus a P2 prime. They are both zero. This is allowed by the linear momentum conservation. That means their relative motion to the center of mass just disappear. Strange. So energy is lost. However, it can be understood as the internal energy of each particle. Each particle is not a single particle, but it consists of many particles. They are connected with some strings, for example, and when they hit together, even though the central mass of each particle makes a complete stop, the particles inside each particle vibrates very fast, rapidly, so the lost kinetic energy is transformed into the internal kinetic energy of the system. So in this way, we understand the energy is conserved. And this kind of energy is called heat. And at the last stage of this semester, we study the heat energy. Okay. Anyway, let's go ahead. We consider the center of momentum frame or center of mass frame for the two systems of particles. And these two systems make a big system of particles. Initially, they are making this. Their center of mass is capital X1, has the velocity, capital X2 dot has the velocity. They collide. When they collide, the total linear momentum is vanishing because for simplicity, we have chosen the center of momentum frame. The kinetic energy is the sum of each particle's kinetic energy. At the final stage, they make a collision, And then each particle has its own energy and its internal energy. This one and this one. Because this is a system of particles. System of particles has a kinetic energy, even though the initial system has no relative motion in its own system. No relative motion in its own system. So we assume that initial state internal energy equals 0. Initial state of internal energy equals 0 for first particle and second particle. But in general, after the collision, we cannot assume that they are vanishing. Instead, they may acquire some relative motion within a system. So the CM, still CM is at some point, and relative to that, each part is vibrating, something like that. So this is the internal energy of the first particle. That particle has its own structure. This is the second one's contribution. But we consider the completely inelastic case, or inelastic case of before that, the in it, because we have considered the central momentum frame, the final state also satisfies the linear momentum conservation. Elastic collision is the case when this true internal energy vanishes. If we have the conservation of total kinetic energy, then we say it is a elastic collision. That assumes that there is no internal kinetic energy for each particle before and after collision. If we can consider a very simple case, but in general, if the collision is elastic at the center of momentum frame, that each particle has its own speed. The speed is invariant. If the system is completely inelastic, then they lose all of the kinetic energy. Then the energy seems not conserved. So each particle does not move at all, then where is the initial energy? It is, if we look at the explicit energy shown by the central mass of each particle, the energy is completely lost. Therefore, we say it is a completely inelastic collision. However, the energy is actually not lost, but it is not explicit. That is implicitly hidden inside each particle's thermal energy, something like that. So internal energy of each particle's, the sum of the internal energy of each particle, that corresponds to this contribution inside each particle's system. That can be only understood. That is the ideal way to understand the lost energy. So energy is not actually lost. Let us consider the two-dimensional elastic collision of two identical particles. In any case, we have a collision of two identical particles, whether it is identical or not. The two particles has the center of mass frame. In that frame, the motion is just one-dimensional. Before the collision, either before the collision or after the collision. So if we have a single straight line that connects the two particles' motion, relative to the center of mass, and we have another line that connects the motion of the two particles after the collision. Therefore, it is in general a two-dimensional case at the center of mass frame. In this frame, and to simplify our analysis, we just use the same mass, identical particles. Then we can only consider the velocity of the four particles, the two particles before and after the collision. The linear momentum conservation has initial momentum ma, mb. These are the initial velocity. So mc plus md. Because all of them are identical, we can erase m altogether. So this a plus b equals c plus d represent the linear momentum conservation. Next, we are considering the elastic collision. So next we consider some of the kinetic energy. That is 1/2 mv squared. So 1/2 ma squared, 1/2 mv squared equals 1/2 mc squared plus 1/2 md squared. We can erase 1/2 of m, and we end up with a squared plus b squared equals c squared plus d squared. We can square the linear momentum conservation relation, a plus b squared equals c plus d squared. We can expand this 2 times a dot b plus b squared, c squared, 2 times c dot d plus d squared. We subtract the energy relation from here. We end up with the fact that we have a dot b equals c dot d. This is true in any frame, but for simplicity, at the center of mass frame, we find the center of mass identical particle. They collide together. C plus A plus B equals 0, and that is C plus D. So A equals minus B, and C equals minus D, and energy conservation gives, substitute everything together, A 2 times A squared equals 2 times C squared, and A absolute value equals B, and C absolute value of D. So absolute value of A, B, C, D are all the same in the same frame. Because this relation is true even in the non-CM frame. Therefore, for another simple frame of reference is the fixed target frame. Fixed target frame is when we play a billiard ball, a stationary particle is hit by another identical particle, and if they make a head-on collision, then one particle stops and the other goes away with the same velocity as we hit the target. If they make some scattering angle, and they are making 90 degrees right angle. But why? Let's see. In a fixed target experiment, A dot B, we have target stationary. So A dot B is always 0. So C dot D is always 0 too. But let's see. First, because C dot D equals 0, C D cosine theta equals 0. So either C equals 0 or D equals 0 or cosine theta equals 0. We say A to C and B to D. If C equals 0, then A hits the ball and then A stops and this ball flies away with the same initial velocity. This is the case. D equals 0, That means B used to be, B becomes D. B used to be 0, but D equals still 0. That means you missed. You throw this ball away, but you missed. So it is the same as the initial state. That's fine. The third one, if C and D are both non-vanishing, cosine theta must be 0 because it is always correct. Cosine theta equals 0, then is angle theta equals 90 degrees. Okay, that's the reason why that kind of phenomenon appear. The next one, the final stage, we consider rocket problem. Rocket of mass m flies and it emits the gas with a relative velocity capital U minus capital U backward. And during at a very short time dt, it loses its mass by this amount. This because this gas has its own mass, and this is a negative value, and alpha is a positive. So it loses its mass m to m plus dm, that is less than m. During that time, the mass is lost, and lost mass acquires a velocity. However, this is relative to the rocket. Relative to the rocket. We have to describe the motion of the system on a reference frame, that is an inertial reference frame. Because it emits the gas, the rocket is accelerating. The rest frame of the rocket is not a good frame because F equals ma cannot be applied in that frame. So we stand up on the Earth on the inertial reference frame and look at this rocket and what is the velocity of the gas. This is relative to the rocket. So to us, it has a different notation, the relative motion of the gas plus the velocity of the rocket. That is the velocity. This is the velocity of the rocket seen from us, and this is the relative motion. So what we see is this minus a small u, that is a capital U, plus velocity of the rocket. All right. So initially, the whole system had the momentum mv. If we look at this rocket, but this is the total linear momentum. We divide it into two pieces, m plus dm and dm minus dm. The minus dm is a positive, and this one is less than m. And it acquires the velocity a little bit, that is v plus delta v. And this gas carries the momentum minus u in the frame of reference. This is a rocket frame, but however, we have to describe, so I have to add this capital V. So this linear momentum, total linear momentum, is indeed conserved, sum of the rocket's momentum and the gas momentum. But we keep track on the velocity and mass of the rocket instead of gas. They are thrown away. So here it is. This is a minus a small u. And minus dm is positive. There is a typo. We introduce a minus u for the gas velocity measured in the inertial reference frame. So, and mass of the gas is a minus dm. So minus dm multiplied by minus u should be there. So let me correct this. So I have corrected the typographic mistake. And this is a positive value, and this is the velocity measured on the ground, and that is this. And substitute this one is identical. This is a v minus u, right? V minus u is substituted, and mass is positive, right? Minus capital U is the velocity of a gas measured in the rocket, and if you measure the velocity of the gas, you have to add the velocity of the rocket, capital V. And minus dm is a positive value. So everything is ready. The initial total linear momentum of the system, rocket gas system. Rocket loses its mass. The dm is negative, loses its mass, and gains its velocity. Okay, that's fine. And the lost momentum is shared by gas. And in here, gas momentum is v minus u minus dm. That is u minus v plus dm. Okay, that's fine. So we expand the right hand side. We have mv, left hand side mv, cancel. And next term mdv and vdm, and small contribution dm dv, and we have udm minus vdm. Vdm cancel. Okay, mv cancel, and we have three pieces. This is the differential, and this is double differential that vanishes in the limit of you mean we had Euler's number, limit n goes to infinity. If I have this one shows the differential. If I have additional piece, a higher order differential, that does not contribute at all. So even if I add 1 over n squared, this one is still e, something like that. So this one is completely gone. Finally, we have mdv plus udm equals 0. Right? So dv equals to dm over m u. So don't be confused. Minus dm is a positive number. And if you look at this figure, gas is going backward with u. So that means u is parallel. U is parallel to the rocket's velocity. Hence, this is a positive, and u is parallel to v. So this change in velocity of the rocket is parallel to v. So it is accelerating. If we can carry out the integration is trivial. This is log integral. So the final value and initial value. The left hand side is just a change in velocity. So final velocity of the rocket is the initial velocity of rocket plus final mass is always smaller than the initial mass. So let me upside down and we flip the sign. Plus u log mi over mf. And mi is always greater than m final. So that's the reason why rocket is boosted up. Today this self-test is relatively easy, and we have introduced already the reduced mass for the two-body system. And this shows that in the center of mass frame, this contribution for the center of mass uh, is treated as a center point particle. This one vanishes. Only the relative motion survives, and relative motion is completely described by the relative coordinate r, that is the difference between the two particles' position, and conjugate momentum of relative conjugate to the relative coordinate is expressed in terms of the reduced mass, that is the product divided by the sum of the two masses multiplied by the time derivative of the relative coordinates. In such a manner, if the energy is elastic, energy is conserved, it is trivial to find that this relative coordinates time derivative, that is the relative velocity of the two particles, should be conserved. That's the reason why the high school textbook, they use the elastic coefficient, something like that, that is closely related to the that is just a reflection of these results for the relative coordinate in concept. But unfortunately, they do not tell you why the coefficient of elasticity is expressed as a relative velocity. It is very stupid to memorize those formulas without understanding physical basis. That is the basis. Finally, you learn. That's it for today.